Hi, this is Olivia Stodig, and I'm going to explain today how to create a parametric composite model to analyze it using CalculiX CrunchiX and to recover the output from this analysis in an automated fashion, which then also allows us to run a parametric study on this parametric model. So let's get started. I'm picking up the code that we had last time, and I have done quite a few modifications to it, a few additions. So I will go through these progressively. So I will start by looking at the new files. So I still have the parametric box.py input file, which is our main script. And then I have a new script called Parametric Studies, which we will look at later. So looking at our parametric box file, we have now got maybe a couple more imports. The important thing here is that we are now using CalculiX. So if you haven't got it installed, please go and get a free version of CalculiX CrunchiX and add the path to the executable here. So it's important, it's called CalculiX. And then we have now got two inputs. So we can now choose between the previous input that we had, which is a Nastran analysis, and a composite analysis using CalculiX. There have been a few additions to the input. So you will see here now that we're listing the element type for CalculiX, the solver to be specified in CalculiX graphics, the solver to choose from our local executes, and a mesh file, which actually for the Nastran case is not used, but it just needs to have some value in here. You can set it to none, so it shouldn't be a problem. So the main thing here for the CalculiX analysis is that now we have the same model, so the same span, chord, airfoil section, and we have now a master file, which is a CalculiX master file. We start off with the same mesh refinement, and we are using second order quadratic elements here. So actually in the last tutorial, I thought this was set to 10, but it was set to 9. So actually previously we were generating linear elements. Here with CalculiX, we need to have quadratic elements to be able to use the composite shell option. Our solver now is CalculiX, which is actually shortened as Abacus ABQ. So it's a very similar format. We are using CalculiX as the solver, and then we are going into the composite definition. So here we are specifying two different composite plies that we have available. One is a 0-degree ply with straight fibers, and the other one is a 90-degree ply with straight fibers in the 90 direction. And we can see here that we're specifying an ID, a thickness in meters, the region where we are applying this ply. So this is related to our section properties, which we will see in a bit. And then we specify two different orientations. So actually, if you look at these two different plies, they're almost the same, except for the orientation. And the orientation is what specifies the main fiber direction. So you can see that for our orientation 0, we have a main fiber direction in the Y direction, whereas for the orientation 90, it's in our X direction. And these properties get projected onto the surface of the model. So these orientations are specified in the global or basic coordinate system of the analysis, and then they get projected to have the right properties on your model surface. Finally, we specify the layout. So we actually have, let's see, 1, 4, 5, 6, 10 plies in this model. It's a symmetric layout. So we should not get any coupling between the bending and the in-plane deflections. Obviously, this is a dummy laminate, so you could specify anything that you want in here. And it's currently applied to the whole model. Then we also specify a new file here, which will be created during the process of creating the model. This is a file which will contain all the composite properties and orientations. All right. So what else do we have? So we have an update to the main function. Most of this will look familiar. However, we have now got one new function call here. So if we have a composite layup in our input, we are now calling the getCompositeProperties function with our input, which will generate the input file with the composite properties, which I just mentioned above here. So this is the file that will be generated. We then run the analysis, which is similar to what we had before. And we now have a new function call here as well, which is getFEA output. So we actually process the output from the analysis and generate some data that we can then either process somewhere else or plot, which we will see later on. Right, so let's look at the first function that we've added. So getCompositeProperties. So if I look at the function, it basically checks whether we have our solver set to CalculiX. If it's not CalculiX, then we get a warning message and this is skipped. So composite properties at the moment are only implemented for CalculiX, although of course you can also do a similar analysis with Nastran and other solvers. So the first thing that we do here is we actually, after the CGX run is complete, CGX outputs elements with this S8 type. However, for a composite analysis, we do require the S8R. So here we manually replace that line in the input file. And then we also generate the input file that I was mentioning earlier. So if we go into this function, we have a function that creates the input commands for CalculiX CrunchiX. And it's very similar to what we've seen with the CGX file previously. So we have some creation of the commands in a data set first, which will then be written to file. And we will see what this looks like afterwards. So this is a standard sort of format. Okay, going back to our main function. So we've covered the getCompositeProperties. Right, so yes, so as I said, once the commands are generated for the CalculiX CrunchiX, we just write them to file, which corresponds to this composite props file. I should probably have mentioned previously that there's a few updates as well to the execute CGX. So if I just have a quick look at that. Sorry, this is just the execution of the CGX. The one that I wanted to look at is getCGX input file. Okay, go to the definition of that. And get commands. Yes, so there's one update here, which is just worth mentioning. So we previously did a normal modes analysis using Nastran. In this case, we're now doing a static shear load analysis in CalculiX. So besides fixing the root, we are also specifying that the loads will be applied to the tip of the wing. So it's a shear load in the negative Z direction. So it's just pushing the wing down. And so we have done some updates here to this get commands function to make sure that the proper files are created. So you will see that we are creating a last node set, and then we're outputting that to a separate file, for example. Okay, the main other thing here that we should look at in our main file, right, was the get FEA outputs function. So if I have a quick look at that, we now have again this if statement here. So it only does something if we have if we're using CalculiX. So at the moment we're not doing anything with our Nastran outputs. And if we do have the CalculiX analysis output, then we can first get all the displacements from the CalculiX output file, which is a .dat file. CalculiX does not have rotational degrees of freedoms on the nodes. So if we do want to have a rotation output, then we do need to calculate that, and we can calculate it from the node displacements and from the original mesh locations. So we do calculate this rotation at an average node on the wingtip, as well as the average displacement on the wingtip. And if you're curious, have a look at these functions. There's nothing too exciting in there. The outputs from our analysis are then for our CalculiX static bending analysis are these 6 degrees of freedom displacements and rotations at the tip of the wing. And then, yes, we just get this back and we can process this further for whatever we want to do. Okay, so the way to run this now is to just choose which input you want to analyze by setting inputs equals to 1 or to 0 here at the bottom. So if it's 0, it's a Nastran analysis. If I set this to 1, then I will do a CalculiX analysis. Okay, so let's have a go at this. So I'm going to run this in our debug session. First, let's have a look at the debug console. There we go. And then we just execute this. Okay, so we've just run our parametric box script using the CalculiX input. So just to remember, this was the input that we used. And here is the output that was generated. So we're now, we've switched off the plotting of the airfoil section. So it goes all the way through to executing the FEM analysis, and then it comes back with this object, which includes our deflections and rotations at the tip and end process. Perfect. So what did we actually generate here? So we can see that we have quite a few new files in our directory. So a few of them might look familiar. So the first thing that we'll see here is that our we have our so the input file that was not changed. This is the master file, and it refers to this composite shell input. So we can see that that has been generated here now, and that's been generated automatically by the script. And we can see that we have our 2 orientations, and also our shell section with 10 plies. So the thing worth noting here is that although we are specifying a shell section, CalculiX internally will turn this into stacked solid elements with different properties. And we'll see that in a bit. What else do we have? We have our CGX input file. This is very similar to what we had using the Nustra analysis. The only difference here is what we set in terms of the element type and the extra outputs that we have here. So the node set for the tip load, and our solver is now Abacus. The node set we can see here, and what else? The mesh file, of course, is now in the CalculiX format. So we have the node keyword at the top, and as we scroll down, we then reach our elements keyword, and we can see that we have this S8R element type here. So we actually have shell elements with 8 nodes per element. Right. And the boundary conditions is very similar to what we had previously as well, but of course now this is in the CalculiX format. So we have boundary conditions in all degrees of freedom at the root of our model. Okay, so what does the output actually look like? So the first thing we can do is in our input file, we can see what output we've requested. So this is now a static analysis with a tip load applied on this and last node set. And the output that we have is in 2 different formats. One is the node file format. So this will actually generate an FRD file, which is a binary. Sorry, it's not a binary file, but it's the file that we expect to open with CalculiX graphics. And the other file, so if I go back to my input file, right. So if I go back to this file, the other file that we're also generating is, well, it always gets generated. It's a .dat file, but we're printing the node displacements to that as well. So this is a bit more user-friendly for visualizing the deflections. So we can see that we have 43 lines. So we have 40 points, 40 nodes where we're extracting the deflections, and we have our X, Y, and Z deflections here. And we'll see that we can process that quite easily. Okay, so if we are curious about the model itself, let's have a quick look. We can actually open this using CalculiX graphics. So you will see whatever your CalculiX graphics path is. You can open this FRD file using the -v option. And here our FRD file is called shear without iteration. Okay. So the model gets loaded. And if I bring this over, this should be what you can see. And then if you want to have a look at the mesh, which we didn't do last time in CGX, you can actually visualize both the mesh and the outputs here. So if I just toggle the element edges, so you can see that we have a quadratic mesh, a quadratic element mesh. So we have 10 elements on the along the chord, and 40. Sorry, I can't remember what value we had, but it was 20 around the airfoil and 40 along the span. Yeah, so it's 10 along the width of the wing and 40 along the span. And if we actually zoom into this, you can see that we don't have a single thickness here. CalculiX internally has expanded this to 10 very flat solid elements. So whether this is something that you want or not is something to think about, but that's not the main question of this this video. So in terms of the output, we have here, we can access the displacements. So we can visualize it both in terms of a fringe plot. So if I just go for all and zoom out again, so we have a nice fringe plot of our displacements along the span. And we can also toggle the displacement, so we can actually see the deformed shape. And now if I view this in a slightly better position, so right, this is looking from the trailing edge towards the leading edge, and you can see that we actually have this slightly deformed shape. So we can even animate this if we want to. Let's see if this works. Perfect. Yeah, okay. So this is actually going negative amplitude, which isn't really what we want. We only have positive amplitude here. Anyway, so this is CalculiX graphics, but of course this is a check of only one model. So if we want to do anything with the data and you're not that familiar with the CalculiX graphics interface, then it might be easier to use the .dat file. Okay, so let's close this again. And so this is where the next step, the parametric study, becomes interesting. So in the parametric study script file, what we're doing is that we import our parametric box script, and we then define two different parametric studies, which we can switch here at the bottom. So the one that's currently selected is this material study. And then we also have a mesh study, which you can look at in your own time. In terms of the setup of these parametric studies, we simply want to look at what happens if we change the rotation angle on our 0-degree ply. So you remember previously we defined in our input here, defined these plies. So we had a ply 0, which referred to orientation 0, and our orientation 0 had its main direction in the global y direction. Now, what we want to see with the study is what happens if we change this default 0 orientation by rotating it around the z-axis by a certain angle. So in this parametric study, we increment this angle from 0. So we start off from the previous analysis and then increment all the way up to 45 degrees. And the rotation is positive, so it means that for 45 degrees, our fibers are running from running towards the leading edge from the root to the tip of the wing. And then we have a for loop which copies the input from our parametric study parametric box file. So we import that input, and then we do a deep copy on it. So we keep the previous version, and on the copy we then set this orientation vector by rotating the previous orientation by a certain angle. So we just use a rotate vector function here, which if I go to the definition, let's see if this works, is simply applying the SciPy rotation on the previous coordinate system. So So this gives us our updated input, and then we run our main function repeatedly and recover the output from each iteration, appended to a list. And then once we have all of that, we can actually plot this data. Okay, so let's have a look at what that does. So let me just delete the previous output. And if we run this, okay. So here we go. So that's the first iteration. So we're now actually running CalculiX graphics. We can see executed the FEM analysis. We recovered the first set, and now we go into the next iteration. And we can see that our orientation 1 that's the baseline, and the next one has got this value, so it's rotated by 10 degrees. And we get the next output, and so on. So we'll speed this up in a second, just so that we don't watch every iteration. Okay, so we've had our 4 iterations. We have all the results, no warnings, no errors. And now we have as an output from this analysis our plot of tip deflection and tip rotation. So that's the vertical tip deflection, and the rotation about our y-axis. So this is like torque along at the torque at the tip, or twist at the tip of the wing. And what we can see here is that, as we expect, if we shift the fibers away from the main wing reference axis, we're actually making the wing more and more flexible. So as we do that, our tip deflection increases. And as we shift the main fiber direction, rotating it forward, we also induce this bend twist coupling effect. So we actually twist the airfoil section with nose down at the tip of the wing as we bend it. So this is just a quick demonstration of what you can do with a parametric model and Python and open source software and solvers such as CalculiX. So thank you very much for watching. And if you have any questions, please feel free to post them on YouTube, on Medium, or on our website. Thank you very much.